Welcome to our first online course. So we're going to pick up where we left off with last time we were together, and we were talking about acids and bases. So we introduced strong acids and strong bases, and so I'm just going to recap very briefly what strong acids and strong bases are. So at the top of the board you can see, remember, they are 100% dissociation reactions. And one thing that is interesting about strong acids and bases is even though these strong acids in particular are compounds that are covalent bonded, they will still 100% dissociate into their respective ions in aqueous solution. Right, so there were 6 strong acids, right? HCl, HBr, HI, and those were our halogen ones. We also had our oxygen-containing acids, which were nitric acid, HNO3, and we also had perchloric acid, HClO4, and our last category, which is polyprotic or diprotic acid, is also an oxygen acid, but I put it in a separate group, sulfuric acid, H2SO4. So those are the 6 strong acids that will 100% dissociate into ions, even though they are held together by covalent bonds. Right, because typically covalent molecules do not dissociate in water. The other class of strong bases were metals from column 1 and column 2 on the periodic table. When they are paired with hydroxide, they will 100% dissociate into the respective ions. All right, so now we're going to talk about weak acids and weak bases. So weak acids and weak bases, they only partially dissociate into ions. So usually only get about 1 to 10% dissociated. So a lot of times we'll show the arrow only a teeny bit going to the product side, and the majority of the equilibrium reaction, which we have going on, is predominantly on the reactant side of the equation. So you can see here we have an equilibrium forms, and that's really important and crucial because it will allow us to calculate any type of problem involving weak acids and weak bases using ice tables. Okay, and so that is pretty significant that anytime we have a weak acid or weak base, we have equilibrium going on, and then we would solve respectively using ice table. So I gave you a flow chart in class before we left, like something like this, right? And so that would be the first thing that we would want to identify when we eventually get into solving problems is it strong or is it weak? And depending on what it is will determine how we will solve the problem. Okay, so just to give you an example of what is a weak acid. So over here is acetic acid, C2H3O2. That is acetic acid that is found in vinegar that we will be using in a titration experiment shortly here as well too. Right? So acid plus water, okay, we will form H3O plus and C2H3O2 minus. So you can see that this weak acid donated a proton ion. Okay, it donated this hydrogen right here to the water molecule. Remember we drew out the reaction mechanism in class the other day, and there's actually a lone pair of electrons on the oxygen there, and this oxygen is actually what takes that proton. So we say that this acid donated a proton because it lost one over here. It does not have one. It becomes the acetate anion that is one of the polyatomic ions that you learned. Okay, the base respectively is water, and so this oxygen accepts that proton. So we say accepts hydrogen proton and becomes H3O plus. Okay, so one thing I just want to point out here is H plus we commonly call proton, but that is not the proton that we learned about back in chapter 1 that is inside of the nucleus. So that's not the same proton we're talking about here. When we talk about protons for acids and bases, we're talking about the acidic proton. Okay, so one thing I just want to draw to your attention here is there are different functional groups. When you get into organic chemistry, you have an alcohol, you might have a ketone, carboxylic acid groups, ethers, amines, things like that. Okay, so a carboxylic acid group looks like this in structure. You have a C double bond O, and that carbon is bound to something else over here, and then you have an OH. This hydrogen that's bound to the oxygen here is the acidic proton, and we call that H plus proton. Okay, And that proton is the one that will dissociate. So that's the proton that will come off into solution, and this oxygen can pick it up and become positively charged for a water molecule. Okay, so here we're showing that this H plus, the proton, is dissociated, and we're left with this C double bond O. Sometimes we denote it shorthand like that. Okay? All right, so the example of a weak base would be ammonia molecule here, and we can see that this ammonia molecule is picking up a proton, right? Similarly to the base water up here, it picked up that proton, became H3O plus. This ammonia here, if you look over here, you can see it picked up a proton. So it's similar in terms of its characteristic of what it did mechanistically. It's going to pick up a proton here from the water molecule and form OH minus, which is 1 minus hydrogen from a water molecule there to give us hydroxide ion. And so bases form OH minus ions as well. All right, so continuing on, next we're going to talk about 3 different definitions that are commonly used to describe or explain or identify acids and bases. Okay, and so your textbook outlines 3 different ones, so I kind of made a little chart here that kind of organizes each 3 of them. All right, the first one is the Arrhenius concept. This is the least general definition that is used, primarily because it is restricted to the definition in only aqueous solutions. You can have acid bases occurring in many other different types of solvents, and so by this particular definition, it does not account for those types of situations. And I just saw a either looked kind of funny because I was missing. Okay. All right. So Arrhenius definition for an acid says the substance that dissolves in water will increase the H3O plus concentration. So we saw in some previous examples that we were forming the H3O plus ion. So by definition, the acid on the reactant side of that equation would be an Arrhenius acid. Okay. If that was in water. All right, a base would be a substance that's, when it's dissolved in water, will increase the OH minus concentration. So if you're forming OH minus ions, then that substance would be an Arrhenius base. All right, and so the neutralization reaction, we have the acid and the base forming the products. H3O plus OH minus ion, or forming water molecule liquid. And then we can reduce that to the net ionic equation. To simplify that without water molecule, it's just H plus OH minus, forming 1 water molecule. So that's the traditional net ionic equation that we learned about for acid-base reactions. Okay. The second definition, that is the most common definition for explaining what is an acid, what is a base, and identifying which one is each in our chemical reaction, is called the Bronsted-Lowry definition, or the Bronsted-Lowry concept. And each of these guys independently came up with the definition on themselves, so they're both kind of credited for this particular definition. Okay, it is not restricted to aqueous solutions, so this definition holds true in any other type of environment that the reaction is taking place in. So, definition that we will use the Bronsted-Lowry definition in our class. An acid is a proton donor. So, if you want to know if an acid is occurring, or which one is the acid in the substance, then you would look at the product side to see if it gave up a proton. If it gave up a proton, an H+, then it donated it to something else. Okay? The base is the one that takes the proton. So that's usually the oxygen on water or something like that, that accepts the proton from the acid. Right, and then the neutralization reaction is just a proton transfer. One is losing a proton, the other is gaining a proton. And again, you would compare the reactants to the product side to see what is occurring for each one. Okay, we take a look down here as an example for a Bronsted-Lowry identification of which one's acid and base. All right, so I already have the answers labeled here, but if you just kind of ignore that for a minute, we take a look at the equation that we left off with on the weak base example that I gave you. Previously, when we were talking about weak bases, I gave you ammonia with water, and we had this ammonium ion and OH minus ion. Okay, and I just kind of told you that this was the base and this was the reaction that occurred. All right, so the question might be something like, well, identify which is the acid and base in this particular reaction. So what you have to do is you have to look at this reactant, NH3, and you have to look at the product that's similar to it. What happened to it? Well, it gained a proton, right? It gained a proton. So did it donate a proton? No. Did it accept a proton? Yes. So based on this definition, Bronsted-Lowry, this ammonia gained a proton or accepted a proton. And so we would label that as the base. Okay, Bronsted-Lowry accepted a proton. Yes, accepted a proton. So this ammonia accepted a proton from where? It accepted it from the water molecule. So the water molecule went from H2O to OH minus. What did it do? Did it donate a proton or did it accept a proton? Well, it lost a proton, meaning that it donated it, it gave it to something else. And so by definition, this is a Bronsted-Lowry acid, okay? And so we're not really looking at the mechanism for this, but this nitrogen actually takes a proton from that hydrogen off of the water molecule, okay, for that. All right, so one other thing that we're going to talk about, we'll come back to here in a minute after we talk about the Lewis acid-base definition, is this conjugate stuff over here that I have on the board. Okay, so the third definition is the Lewis acid-base concept. This is primarily definition used in organic chemistry, also in coordination compounds where you have metal complexes and things like that. And the definition for a Lewis acid is it's an electron pair acceptor, so it accepts electrons. And the base would be it's donating electrons, electron pair donor. Okay? And then this is just the reaction would just be an electron pair transfer reaction. Okay, all right, so the last part here that I want to talk about is this conjugate acid conjugate base that we have labeled here. So because we have an equilibrium reaction, we can go in the forward direction or we can go in the reverse direction. So if we're going in the forward direction this way, right, I look here to see what's happening to ammonia. Oh, it's gaining a proton. Bases accept protons. This is a base. Therefore, this is the acid. What did the water do? It lost a proton. It donated it. It donated the proton to the base. Acids donate. Bases accept. Okay, so this direction, we have labeled them as base and acid. However, if we go this direction, so now these are the reactants and we're going to products that direction, what we can do is if I've identified that this is the base here, then this is the what we call the conjugate acid. So it's only differing by a proton. And so in this direction, what does it do? This went from NH4 plus to ammonia. It lost a proton. What loses protons? Things that donate. Acids donate. So this is the conjugate acid. That was the base. So acid base, pair up, right? And then this was the acid here. So in this direction, went from OH minus, and it gained a proton. Acids donate, bases accept. So this accepted a proton from here. So it's conjugate base. This is the base, this is the acid. Conjugate acid-base pair. Okay, so down here is kind of a summary, the NH3 and the NH4 plus compared to H2O and OH minus. Both of these substances differ by just a proton, an H plus ion. Okay, they're called conjugate acid-base pairs. Okay, and again, so it's just going the forward or reverse direction. Strong acids will have weak conjugate bases. Likewise, strong bases will have weak conjugate acids. Okay, so now we're going to do a couple of examples, just identifying the acids and bases and the conjugate acids and the conjugate bases of some examples. And then I think I have a handout for you to do a couple more problems on your own. Okay? All right, so take a look at this first example here. This is the acetic acid molecule that we looked at just recently. And so we have acetic acid with water and we form some products over here. All right, so the first thing that we want to identify and see is we want to compare this substance to the like substance over here. And so you can see it's just differing in a proton. So these are going to be conjugate acid-base pairs. What's happening? This lost a proton, and probably what I should put on the board is acids donate, bases accept. Okay, so acids donate. Did it donate? Yes, it lost it. It gave it to something else. So this is an acid, and therefore this would be the conjugate base of that, if we're going the opposite direction. And then that means the water molecule has to be the base. What did it do? It gained that proton from the acid and became protonated. Bases accept. So yes, it accepted, the water accepted, and therefore is a base. And then paired up with this differs by 1 proton, so going this direction it would be the acid form, going the reverse direction, so this is the conjugate acid. All right? Okay, so take a look at the next example here. We have the C6H5OH with the C2H5O minus, and then the products over here. What did the C6H5OH do? It lost a proton. So bases accept, acids donate. It donated a proton, it lost it, it donated to something else. So acids donate, right? And then this would be the conjugate base going the other direction. This substance here picked up a proton, acids donate, bases accept. It accepted a proton, right, by looking at the product side. So this is the base, this is the conjugate acid there, right? Okay, and then the last one here, we got water plus a Cl minus ion. And on the product side here, we have HCl and then OH minus. You can see from my arrow here, I have one directional arrow going to the left because this is HCl. This is a strong acid. So 100% it will be dissociated into those product ions over there when this reaction is occurring. But if we just start over here like this is a reaction, maybe you don't notice that initially. You say water molecule goes over here. So what does this do? This lost a proton, so it donated a proton, right? That's the definition of a acid. Acids donate, bases accept. So then this is the conjugate base. And the Cl minus here is gaining a proton, so it's accepting a proton. Acids donate, bases accept. And this is the conjugate acid. And of course, this is the acid, right? It's donating a proton to the water, right? Becoming dissociated over there, so it's the acid going on that direction. And again, it is one directional here. Okay, so another thing that I just want to point out and talk about briefly here are some substances can behave as both acids and bases, and those are called amphoteric species. So there are species that can act as both an acid or a base. It depends on what the reaction is that they are reacting with. And in the examples that I have starred up here above, this first one and the third one here with the water and the HCl, if we take a look at water in those examples, in the first example here, water is a base, right? But in this example down here, water is an acid. And so this is just an example that water is an amphoteric species. So depending on what it is, it can be an acid or a base. So you can't just always say, oh, I know this is always going to be a base or an acid. Well, not exactly. You always want to kind of do this analysis to figure out what's the acid and what's the base whenever you're labeling and identifying things. Okay? All right. Another example of an amphoteric species is a bicarbonate ion, HClO3. And so I think there is an example and a handout that we're going to practice writing the bicarbonate ion as an acid and then practice writing it as a base. Okay. All right, so now we're going to continue on with the first handout that I gave you in class from chapter 16. This is the handout that we're going to take a look at these example problems. Look like this. Okay, so we're going to work through these real quick. Just going to take a look at the first page. All right. So on the board up here, we just have a reminder what is an acid and what is a base based on Bronsted-Lowry definition. Right, so acids donate a proton, bases accept a proton. And so the first question here says for each reaction, determine the conjugate acid-base pair and then their relative strengths. So we've not really talked too much about determining relative strength here, so we'll just kind of introduce that a little bit. All right, so identify acid-base and then the conjugate acid-base pair. All right, so this first one here, remember we'll have to look at the products to see what's happening. So this HSO4 minus turns into a SO4 2-. So it is minus a proton. So it lost a proton or it donated a proton, therefore it is an acid. So this is the acid, and since it's only a difference of a proton, then its conjugate base would be the SO4. Yeah? Okay, and then that means this substance here, which is the acetate anion from acetic acid, is to gain a proton, so it accepted the proton from the acid, accept proton. That is the definition of a base. So this is the base, and then this would be its conjugate acid form. So again, if we're going in the reverse direction, this species is the acid and donates it to that, but this is really the oxygen that takes it off when we're going the reverse direction. All right, so the next one, HCO3-, we are losing a proton, so this is donating it to the other species, or likewise, this is actually, the fluoride ion is actually taking that. So acids donate, right? It lost a proton, and so that is the definition, acid donate, definition of an acid. And then this would be the conjugate base, and this accepted a proton, and that is the definition of a base. And this is its conjugate acid. All right, next one, NH4 plus ammonium ion goes to NH3. What did it do? It lost a proton, it donated it. So again, this is the acid, and this would be the conjugate base. And then this, actually these lone pairs of electrons on the nitrogen here take one of those protons, so accept or take is the definition of a base, and this would be the conjugate acid for that species. Okay? All right, so the next question on the example handout form, we're going to practice right reaction equation for this oxalate anion here, HC2O4-, as an amphiprotic species. So first we have to remember what an amphiprotic species is. That is something that can act as an acid or base, depending on what it's being acted with. In this example here, we're just going to react it each time with just a water molecule. Okay, so if I want the oxalic acid, acetate anion to act as an acid, acids donate a proton. So if I'm just reacting that with water, then it's going to donate that proton to the water molecule. Or likewise, when we talked about the mechanism, the electrons on oxygen are going to take that proton mechanistically. So we're going to be minus a proton on the product side here, right? If this is an acid, it donates. So then over here on the product side, it would be minus a proton, and then that would give us a -2 charge. So we're already at -1, we lose a +1 charge, now we have a -2. And then we have the water molecule that takes the hydrogen and becomes H3O+. That. All right? Okay, so acids form H3O+. That's one of the definitions of a Arrhenius acid, right? Okay, so we want to now write it acting as a base. So bases accept a proton, okay? So one of the oxygens here on the species is going to take a proton from the water molecule. So when we do that, it's going to become H2C2O4 neutral, because we're gaining a plus charge from the, I was going to write this in orange. H2C2O4 neutral. And what's left over, it took a hydrogen from the water, so now we have hydroxide ion. So again, definition, Arrhenius definition of a base is forms OH- ions in aqueous solution. And so that's what that does when it acts as a base. Okay? All right, so the last problem on the handout is we're going to practice writing conjugate acid-base species without particularly writing out the entire reaction equation. So here, we're going to write the conjugate base of this acid. So if this is a reactant, then I want to write the product conjugate base of it. So if this is an acid, acids donate, then on the product side, it would have lost one of the protons. So it would be minus a proton. So the conjugate base of this would be minus a proton because it's donating it. So we would have PO4 3 minus, because we've got minus a proton that is now gone, right? So here, this species, right, is an acid, and we want to write the conjugate base of it, so it's going to be donating a proton. So the first thing you want to think about is, oh, which of these hydrogens is going to be the one that's going to be donating? Where is that positive charge residing at? Is the positive charge on the carbon, or is the positive charge on the nitrogen? And we should know that carbon only has 4 bonds. It can't have, will never form 5 bonds, which would give it a plus, just scratch that. We know that ammonium ion is NH4 plus, and so there's 3 hydrogens on the nitrogen, and one of the other bonds on nitrogen goes to the carbon, so then the positive charge is on the nitrogen. So the hydrogen on the nitrogen is the one that's going to come off, okay? So if this acts as an acid, it donates, and the hydrogen that comes off is the one of them that's on the nitrogen there, okay? And then ammonia, we know ammonia typically acts as a base, but in this example we're pretending that it's acting as an acid. And you can make it act as an acid in certain conditions. And so it would be losing a proton, and so we would, we're at neutral here, so if we lose a +1, now we're at a minus there, okay? All right, and then here we're going to practice write the conjugate acid of each of these if they're base, acting as a base. So the first one, HASO4 2 minus, bases accept, so we're going to be accepting a proton. So on the product side of that reaction, we're going to have another proton added to this species here if it's acting as a base. So the conjugate acid's getting that proton. Okay, so this is H2, ASO4 minus. So this is -2, I gain a +1 charge, so now it's just a minus. And now we're going to have HIO neutral, because I gained a +1, takes that away. And then here I'm going to have OH minus hydroxide ion there. Okay, so the example problems that we just finished, I realized that I forgot to talk about problems 1, 2, and 3, talking about acid strength. It says to determine the relative strengths. So we've not talked about acid strength yet. That's what we're going to get into right here shortly. But one thing that you want to notice is if the direction of the arrow is indicated in the reaction equation, the larger arrow is pointing that it resides more to that particular side of the reaction equation. Okay, so we know that strong acids completely dissociate, or stronger acids will push the dissociation or equilibrium to the other side because they will dissociate more. Okay, so if we look at the arrow here, it's more heavily resided to this side. So the strong side will dissociate more to the weaker side, right? And so here we can say this is the weak side, and this is the strong side for this reaction. Okay. This reaction here, HF, is stronger than this HCO3 because the arrow is telling us it's heavily pushing more towards that side. So this is the strong side dissociating more to the weak side. So I think on our previous lecture we talked about that strong acids always dissociate to the weak side. The equilibrium always resides to the weak side. All right, and then here we're going strong arrow that direction. So this is the weak side. this is the strong side. Okay, if the arrows are not given, you would have to be given some other information about the species and the reaction equation. So if you turn in your textbook in the second edition on page 714, there is a table right there. Okay, that table, okay, ranks, it's figure 16.12. It ranks all of the species and their acid strength or their base strength. So again, strong acids have weak conjugate bases and strong bases have weak conjugate acids. And so some of these you don't maybe not know which, they're both weak species, and so you don't know which one is stronger or which one is weaker than the other. You can use that table to kind of be able to rank them to figure out the acid strength. The other way that we can figure out acid strength is on the Ka number, the equilibrium constant association for the acid, and so we're going to get into talking about that here shortly.